Hello, this is the third and last lecture on special relativity. There's actually a lot more that we could explore because the subject of special relativity is very interesting. However, this is college physics and there's so much that we can do. So what I've tried to do, I hope, is to give you an introduction to a very interesting subject, and you can go and explore some more. In the last two lecture videos, I showed you that Einstein derived from two very simple postulates the following: that if two different observers were to measure the time interval between two events, or the distance from one point to another, the length, then they will get entirely different results depending on the state of motion of the observer with respect to the two events being measured or the distance being measured. We can summarize this as follows. So if you consider one observer in a spaceship that's moving at some speed v, let's say this is our observer, and let's call this observer A. So observer A has in the spaceship a table, and she also has a clock. So with the clock, she can measure the time intervals between two events. And she also has a meter stick with which she can measure the length of the table. So when she has performed these measurements, she writes that the time interval between the two between the two events is delta t naught, which you recall we call proper time. Because she is at rest in the frame of reference in which these two events occurred, and they occur right in her location. So the time that she measures is proper time. When she measures the length of the table, she measures a proper length. Once again, she is at rest with respect to the table. So the length that she measures is proper length. However, for observer B, who is earthbound, who is measuring the time interval between the same two events. Let's say this is the ticking of the clock, and he's also trying to measure the length of the same table. He writes two very different things. He writes delta t for the time interval and writes L for the length of the table. And Einstein then showed that these quantities are related as follows. Delta t is given by gamma times delta t naught, and the length L that observer B measures is given by 1 over gamma times the proper length. This is what we called the consequence of time dilation. This is the second consequence that we derived, and this here is length contraction. And in these equations, gamma, of course, is 1 over the square root of 1 minus v squared over c squared. By the way, gamma is also often called the Lorentz factor. So if you come across this in a textbook, it means the same thing. The Lorentz factor is gamma. And one more thing before we move on. Gamma is often written as 1 over the square root of, instead of v over c squared, we can write this as beta squared, where beta is v over c. And you see that, of course, this is a dimensionless parameter. It's the speed divided by the speed of light. So it's dimensionless. So beta is often used, and it's called the speed parameter. Also, I try to give you an idea of why the effects of special relativity are not apparent to us in everyday life, because everyday life involves speeds that are extremely slow compared with the speed of light. However, when the speeds begin to approach the speed of light, then the effects of special relativity become apparent. When v is about 10% of the speed of light, then you begin to see the real effects of special relativity, which tiny particles such as electrons and protons can acquire. So we often take v greater than or equal to 10% is 0.1 c as the threshold for switching from the classical theory to Einstein's theory of special relativity. Special theory of relativity. To say that the speed is 0.1 c, 0.1 c means that when the speed is about 310 to the 7 meters per second. And let's see what gamma is then. In that case, gamma will be 1 over the square root of v over c is now 0.1, and we square that, so this becomes 0.01. This gives us 1 over the square root of 0.99, which if you do the calculation, you get something like 1.0050 something. Okay, so when gamma is of this, gamma is at this level, then the effects of special relativity must be taken into account. Above this threshold, if you do not use the new equations that Einstein derived, if you use the classical formulas for the linear momentum of a particle or for the kinetic energy of a particle, then in fact you find that the laws of conservation of momentum and conservation of energy and other laws are violated. So, in order for the laws of physics to remain valid in all inertial frames, Einstein had to proceed to derive a whole set of new formulas for the momentum and the kinetic energy and the total energy and you know, other things. For this lecture, we shall just write. We will not derive these equations, we shall simply write the new formulas that Einstein gave us for momentum and for kinetic energy and for total energy of a particle. And that should be sufficient for us in chapter 28. So this is what we shall proceed to do next. So let's begin by writing the new formula for the relativistic momentum, the new formula that Einstein gave us. So in college physics 1, you learned that if a particle of mass m moves at a speed v, then it has linear momentum. And the magnitude of the linear momentum, you recall, is simply a product of the mass and the speed, m times v. And it has units of kilogram meter per second. Momentum is a vector quantity, so the formula that I've written here is just for the magnitude of the linear momentum. Because of what follows next, I will now rewrite this as P is m not v, and I'll explain this in a second. Einstein showed that in order for the law of conservation of linear momentum, which must be applied when particles collide with each other, if this law must remain valid, then the linear momentum has to be redefined in the following way. So I'm going to just write this out for clarity. So in order for the law of conservation of linear momentum to remain valid in all inertial frames, the momentum has to be redefined as follows. Einstein showed that the new formula must be gamma m naught v in kilogram meter per second. And in this formula, obviously, P stands for the linear momentum, which we shall call the relativistic linear momentum. P is the relativistic momentum. Usually when I say momentum, I also mean the linear momentum. I often say the linear momentum so that we are clear that we are not describing the angular momentum, okay? But you can just leave this as the relativistic momentum. That's sufficient. Gamma, of course, is the Lorentz factor, 1 over the square root of 1 minus v squared over c squared. V is the speed of the particle. And now I come here to explain why I put a little subscript on the mass m. M naught. This is the mass of the particle as measured by an observer who is at rest with the particle. So in other words, it's the rest mass of the particle. Okay, it's the mass of the particle when essentially it is at rest with respect to the observer. So we call this the rest mass. Of the particle. And it has obviously units of kilograms. The rest mass is something that you know already. As an example, the rest mass of the electron, this is the number that you know already. If you look at the textbook, the mass of the electron written is actually the rest mass of the electron, and this is 9.11 10 to the negative 31 kilograms. Or the rest mass of a proton. This is 1.6726 10 to the negative 27 kilograms. Last example, the rest mass of a photon of light. I know we have not discussed photons yet, but I'll just mention it now anyway. So the rest mass of a photon, not a proton, but a photon. A photon is the quantum of light or of electromagnetic radiation, which we shall discuss in chapter 29. The rest mass of a photon is 0 because a photon cannot be at rest. A photon is a quantum of light, a small tiny packet of energy of light. And light is constantly moving at 310 to the 8. Light does not stop. So the rest mass of a photon is 0. So let's do a quick example with the calculation of the relativistic momentum for the particle. So as an example, if we were to calculate the momentum of an electron using the classical approach, then the momentum would simply be 9.11 times 10 to the negative 31 times the speed of the electron. Now let's assume that the speed of the electron is 0.9 times the speed of light. So then this will give us 0.9 times 3 10 to the 8 meters per second. So for V equal to 0.9 times the speed of light. Okay. If we do the same calculation using Einstein's relativistic formula, so this is special relativity, we get P is gamma m naught V, or gamma, and we did this a couple of times in the last lecture. When the speed of a particle is 0.9 times the speed of light, gamma is about 2.294. So I'll just simply code it. So this becomes 2.294 times 9.11 10 to the negative 8 times 0.9 times 3 10 to the 8. Okay, kilogram meter per second. Okay, so you can see that between these two formulas, there's a factor of 2.294. So if you did not know special relativity and you insisted on doing your calculations the old-fashioned way, the classical way, you would be off by a factor of as much as 2.294. Make a word of caution before we go on to define anything else. Sometimes, especially in older textbooks, you might find that the relativistic linear momentum is written as mv, where it is understood that m is gamma m naught. So in other words, they've written this, they have written m in place of the product of gamma and m naught. And obviously, since gamma is always greater than 1, except for the case where V is 0, which is non-interesting anyway. So gamma is greater than 1. So m here is greater than m naught. And m is then called the relativistic mass. And I caution you as follows. This gives the wrong impression that as the particle's speed approaches the speed of light, somehow the particle's mass has increased, as in the particle has accreted some more matter into it, or some more molecules or atoms or something. Totally incorrect. There's only one mass, and that's the rest mass of the particle. When the particle begins to move, the only way you can measure its mass is by watching it collide with other particles. In doing the collision phenomenon, only the momentum of the particles become important. So stick with the momentum. It's better to stick with the momentum than to talk about the mass of the particle. So there's only one mass, and that's the rest mass of the particle. So for all times, please stick with the momentum of the particle, not the mass. Okay. Second point. Notice that let me title this the ultimate speed. Notice that the momentum is gamma m naught v, the relativistic momentum. And of course, this here is 1 over the square root of 1 minus v squared over c squared times m naught times v. Question is, what happens when the speed is exactly equal to the speed of light. Assuming that that could happen. But what would happen then? What's the momentum then? Well, let's calculate it. When v is the same as c, then v squared over c squared is exactly 1. Then in this case, the momentum becomes 1 over the square root of 1 minus 1, which is 1 over 0, which is infinite, which is completely non-physical. It's not possible for the momentum to be infinite. And it is therefore correct to conclude that the speed of a particle cannot reach the speed of light, because otherwise the momentum will be infinite, and that doesn't make any sense. So we can conclude two things from here. And number one is that the speed of a particle can never reach the speed of light. And in fact, in this very natural way, Einstein has explained why it was never possible for the electron to be accelerated past 0.9999 times the speed of light. This is what I discussed in the very first video. This is what prompted Einstein's analysis on special relativity in the first place. So the speed of a particle cannot reach the speed of light. But number two, the speed of light is the ultimate speed in the universe. Okay? All right. 3. Let's now look at the kinetic energy. So we shall now discuss the relativistic kinetic energy. And once again, we shall begin by stating the classical formula. And in college physics 1, once again, you learned that the classical formula for kinetic energy is 1/2 mv squared. And because we have defined the rest mass, I shall use it here. So 1/2 m naught v squared. And it has units of joules. Okay, this is the classical formula. Einstein showed that in order for the work kinetic energy theorem to be true, to remain valid. And by the way, the work kinetic energy theorem is an example of a conservation of energy law, right? So in order for the work kinetic energy theorem to remain valid, Einstein showed the following, that kinetic energy must be redefined as follows. By the way, when I say redefined, I mean that he had to actually derive it from first principles, from his postulate. So kinetic energy must now be written as gamma m naught c squared minus m naught c squared. This is the new formula that Einstein gave us. And so this is the relativistic kinetic energy. Immediately you observe that this formula has two parts, one of which does not even depend on the speed of the particle. The speed of the particle v is contained in gamma, in the expression for gamma. This does not even contain v. So Einstein here has showed that when a particle is at rest, even when the particle is at rest, it does have some energy. that energy is given by its rest mass times c squared. And for this reason, we shall call m naught c squared the rest energy of a particle. And we shall use the symbol uppercase E sub naught and write this as m naught c squared. This is the rest energy of a particle. And by the way, if you do not write the zeros, this is Einstein's most famous equation, E equals mc squared, which demonstrates the equivalence between energy and mass. Given a certain mass, you can get a whole lot of energy because c squared is 9 10 to the 16. Given a tiny bit of mass, you can get a lot of energy. Equivalently, if you store energy into an object, then you increase the mass of the object by this relationship. But we shall write it with the subscripts. So that's the rest energy. Let's do an example of a calculation for the rest energy. And let's use the example of an electron. So for an electron, the rest energy would be m naught c squared, which the mass of an electron is 9.11 10 to the negative 31. And we shall multiply this by c squared. Because we want to do a precise calculation, I will not use 3 10 to the 8. We shall enter 2.99792 times 10 to the 8. And of course, we shall square this. Okay, let's attempt to do this very quickly. So it's 2.99792 to the 8. We square that, and we multiply this by 9.11 10 to the negative 31, and that gives us 8.1876 10 to the negative 14 joules. But very often we do not quote these values in joules. Instead, we quote them in EV or in MeV. You recall from an earlier chapter that 1 EV, 1 electron volt, is 1.602 10 to the negative 19 joules, which means that 1 MeV, and M here means 10 to the 6. So 1 MeV is this number here, 1.602 10 to the negative 19 times 10 to the positive 6, and that gives us 1.602 10 to the negative 13 joules. So we can express this number here in MeV by simply dividing this number by that. And so we get that the rest energy of an electron is this here divided by 1.602 to the negative 19. And when you divide this, you get 0.511 MeV. This is the number that you will typically find when physicists are speaking of the rest energy of an electron. They usually quote the result in MeV, and you'll find 0.511 MeV. If you do this, so let's be precise, this is for the electron. If you do this for the proton, then you get that the rest mass of a proton is 938.27, which we shall write as 3 MeV. This is for the proton. Okay, this is how you would do your rest mass calculations. Now let's write the expression for the total. Oh, before I move on, notice that I said that the kinetic energy is gamma m naught c squared minus m naught c squared. You can factor out the m naught c squareds and obtain, so m naught c squared into gamma minus 1. So it's very common to write the kinetic energy as gamma minus 1 times m naught c squared. And you can see immediately that the kinetic energy, since this here is the rest mass, the kinetic energy can be written as gamma minus 1 times the rest energy of a particle. The kinetic energy is gamma minus 1 times the rest energy of the particle. All right. Let's now write an expression for the total energy of the particle. And we're writing this expression for the case when the potential energy is 0. When the potential energy is 0. So if we rearrange this equation here, then this gamma m naught c squared, if I move the m naught c squared to the other side, we get the following. So gamma m naught c squared is the kinetic energy of the particle plus m naught c squared, or it's the kinetic energy of the particle plus the rest energy, which clearly means that gamma m naught c squared is the total energy. So we're done with the derivations. So the total energy can be, not the derivations, we have not derived anything, we've just simply written out the equations. So the total energy is gamma m naught c squared. And once again, you can see that we can write this as the total energy is simply gamma times the rest energy. Do not forget these relations. Okay, gamma times the rest energy. I believe this is the set of equations that we will find useful. So we're not going to write anymore. This is it. So I'll do a couple of problems to demonstrate how we can use these equations. And this time, I'm going to help you with some of the problems on homework 11. All right. So I'm pretty sure that you can do a lot of the problems based on the first two lectures, but the last part of homework 11 uses these ideas. So I'm going to help you with a few of them. Okay? So I'm going to begin at question 12. It's a multi-part question, but it says the following. The total energy of a particle is 4.34 times its rest energy. 4.34 times its rest energy. Question. The mass of the particle is 3 10 to the negative 27 kilograms. 3 times 10 to the negative 27 kilograms. Find the particle's rest energy. And you're given that the speed of light is 2.99792 10 to the 8 meters per second. And you're also given a conversion factor to use, but you can do that anyway. You know how to do it. so the total energy of a particle is 4.34 times its rest energy. By the way, notice immediately, let's try to write this out. It says the total energy, so E is 4.34 times its rest energy. But look here, the total energy is gamma times the rest energy, or total energy is gamma times the rest energy. That's what we've done here. So if we write this side by side, gamma times the rest energy, that immediately tells you that the information provided by the very first line is that gamma is 4.34. Okay? All right. Then it says find the rest energy. Well, the rest energy is m naught c squared. So we just put in the numbers. The mass, the rest mass is 3 10 to the negative 27, and then we shall multiply this by 2.99792 10 to the positive 8, and then we square the result. I'll do one for you, and I'll leave the rest for you to do. So this is, so we get 2.99792 to the 9, and we square this, and we multiply this by 3 10 to the negative 27, and that gives us 2.696 257 10 to the negative 8. Do not forget, this is in joules, and we need to convert this to MeV. They want the answer in MeV. And you recall the conversion factor is that 1 MeV is the same as 1.602 10 to the negative 13 joules. So our rest energy then becomes 2.6962557 10 to the negative 8 joules times, this is 1 MeV per this much joules. So we show this is MeV on the top per 1.602 10 to the negative 13 joules, so that the joules cancel out and the result is in MeV. So I divide this by 1.602 negative 13, and that gives us 1.683 1.683 10 to the third. See, 10 to the third MeV. You can check these numbers when you go home, okay? All right, this is 3 10 to negative 27. So yeah, please check these numbers when you go home. All right, I mean, not when you go home. I'm talking to you like you're already home, okay? All right, then the next question says, see, 2.69 is what we got here. This is 10 to the negative 8, and we divide this by that, and we find the result. It's 1683.01. This, okay, some terms here. All right, so the next question, I'm going to erase part of this now. All right. The next question is, with what speed is a particle moving? This is question 13. With what speed is the particle moving? Okay. Well, gamma is 4.34. We made this point So this here is gamma. So, and gamma is 1 over the square root of 1 minus v squared over c squared, and that's 4.34. And once again, the best way to proceed, as I suggested to you last time, is to square both sides to get rid of the square root sign. So when you do that, you get 1 over 1 minus v squared over c squared, and that's 4.34. Square that, and that gives us 18.83560. We find the reciprocal so that we can, let's continue here. So when we find the reciprocal, we get that 1 minus v squared over c squared is 5.309095 10 to the negative 2, and therefore v squared over c squared is the same as 1 minus 5.309095 10 to the negative 2, which gives us 0.946909, and then you do the square root of both sides to get your v over c, and that's 0.9730925, and clearly then your speed v is 0.9730925 times 2.997992 10 to the 8, and you get your speed in meters per second. I think you can do the rest of them. There's one that may be a little challenging, and I'm going to skip this to question 15. Question 15. Question 15 says the following. I can erase this. Let's erase this. By the way, question 14 says determine the kinetic energy of the particle. You can do that. We've already found the rest energy in 12. Question 15 says, what is the particle's momentum? Now, this will be a straightforward problem if the momentum was needed in kilogram meters per second. This will be the correct formula, and it will be straightforward to calculate it. However, the question wants you to quote the answer in MeV per c. MeV per c, where c is the speed of light. And this is not here, because this gives you a very different unit, SI unit. This is the SI unit. This is a non-SI unit, but this is an equivalent unit. So to do this, I'm going to tell you about another equation that Einstein gave us. And it goes something like this. You do not have to know this, but simply because we have this question on the homework, I'll go ahead and do this for you. So one of the other equations that Einstein gave us was that the total energy squared, E squared, is P squared C squared plus M naught C squared squared. In other words, the total energy squared is the relativistic momentum squared times the square of the speed of light plus the rest energy squared. And recall that the total energy itself is gamma M naught C squared. So let's use that here. We're going to square this. And so this gives us gamma squared M naught C squared squared is P squared C squared plus M naught C squared squared. So now if you look here, we have M naught C squared squared, and we have M naught C squared squared. So group those on the same side. So when I bring this here and factor out the m naught c squareds, then I get gamma squared minus 1 times m naught c squared squared, m naught c squared squared, and that gives me p squared c squared. So if I take the square root of both sides, then I end up with, let me write this on the other side, then I get pc is the same as gamma squared minus 1 to the 1/2, in other words, the square root of gamma squared minus 1, simply multiplied by m naught c squared. So if you do the numbers, if you're more comfortable, I'll just write this as the square root of that, okay? All right. M naught c squared, this is simply the rest energy, and you have found that already, so you don't have to recalculate it. You found that in question 12. So this becomes gamma squared minus 1 times the rest energy. And suppose that your rest energy was written in units of MeV, which is what we actually did. Then finally, the momentum is simply obtained by dividing both sides by C. So we get that the momentum, the relativistic momentum, can then be written as the square root of gamma squared minus 1 times the rest energy, where the rest energy is now quoted in units of MeV per C. So you do not have to write this properly. So this here is MeV per C. This is the unit. Do not then further divide by the speed of light. It's already contained in the unit. You have found this. So your linear momentum then becomes, for the numbers that we were given, this will be the square root of 4.34 squared minus 1 times our rest energy. And I forget what number that was. And then you just quote it here, the rest energy. I think the rest energy was 1.6, what is it, 1.6803 MeV or something like that, whatever it is. And then it's already in units of MeV per C, okay? That gives you the momentum that you're looking for, the relativistic momentum that you're looking for. All right, I wish I had a bit of time to demonstrate one last thing to you. This is called the correspondence principle, which says the following. We know very well that the laws of classical physics have worked very well for hundreds of years, but as long as the speeds involved are low, much slower than the speed of light, Einstein essentially replaces these equations with more general equations that work all the time, whether the speed is low or the speed is high. And the correspondence principle essentially just says that this must be the case. If you have a superseding theory, the theory must at least replicate the correct answers that we obtained at the old-fashioned level, okay, the classical way. We must we must be able to reproduce the old results. And in fact, I could use the example of the relativistic kinetic energy to show you that if you write that expression and you do a binomial theorem expansion, then you can show that the relativistic kinetic energy does indeed reduce to 1/2 mv squared for speeds that are very low compared with the speed of light. But we will not have time to do that. So this is the end of the discussion of Einstein's ideas. Of course, as I said before, excuse me, there are many, many more things that we could have explored, but we simply did not have time. So this should be enough. And the next lecture will look at the beginnings of the quantum theory and how we were able to develop a new model for the atom. Okay, and that leads us to the discussion of quantum mechanics. All right.